Hello everyone, my name is Hafizur Rahman. I am a PhD student in WCS department. So today I am here to discuss the review articles which is published in Nature Nanotechnologies in January 2014. And the title of the topic is Silicon Nanostructures for Photonics and Photovoltaics by Francisco Priolo. So before getting in detailed description about these articles, I would like to give a short and brief summary about these articles. So let's start with the summary. So in this review article, the main topic that has been discussed is the silicon as a high performance material. The main topic is the silicon as a high performance material for photonic industries. We know that silicon has been established long ago as a material choice for microelectronic industries. But this is not yet true for the photonic industries because there are two main constraints of the silicon, that is its limited degree of freedom in material design, which is and the second one is the indirect band gap, which are the two major constraints of silicon to use as a high performance material for photonic industries. But in this review articles, they have discussed some of the recent developments, especially enabled by nano scale engineering for electronics and properties that actually change the picture in a sense that now silicon nanostructures, few of the devices such as silicon nanocrystals, silicon nanowires, and photonic crystals, they are the functional nanostructures which enhance or which even exceed the performance of their equivalent indirect direct band gap materials. So there, in these articles, the two focusing areas are the communication and the photovoltaics. And in this article, they have discussed the recent progress of all these three nanostructures, silicon nanostructures, and they have discussed the state of art in each field, and they have highlighted the challenges that are required to overcome to make the silicon as a truly high performance photonic material. So for communication and for photovoltaics, they have discussed some electrical driven devices, optical devices, and some optoelectronic devices. For communication, they have discussed the electrically driven devices based on the nanocrystals, silicon crystals, and silicon nanowires. In the here you can see that the schematic of this is the schematic of the field effect electroluminescence mechanisms in silicon nanocrystals. And here you can see the emission microscope image of typical silicon nano crystal electroluminescence device, showing the uniform emission of emission that is red color over the whole device area. So the second one here, you can see this is the showing the size dependent shift of photoluminescence by silicon nanowires with different diameters, uh, different diameter owing the quantum confinement effect. And here this it shows the schematic of electroluminescent device using p-type silicon nanowires. Similarly, uh, for communication, the second type of devices they have discussed are the photonic crystals. So here they have in this diagram they have shown the photonics. They discussed the photonic crystal-based waveguide, which is used for the emission of third harmonic generation, uh, and it is operated at the slow light regime. Here you can see that this is slow light regime, and it emits the third harmonic generation. And similarly, silicon-based photonic crystal nanocavities, they can be used to generate both the second harmonic generation and the third harmonic generation in the far field, optimized silicon using silicon nano for photonic crystal nanocavities. And if we go towards the photovoltaics, we can see that in the photovoltaics, the here they have shown the supercells to trap the light, and they have used the binary gating structures to trap the light. Similarly, here they have used the photon cutting and pasting mechanism to uh, to enhance the absorption of the solar cell uh, using the device known as solar sharper. Solar sharper is a device that converts the incoming broadband signals uh, into the new spectrum that is narrower and better optimized for absorption by single junction solar cell. This would require this means the solar sharper require the mechanism of cutting of high energy ultraviolet photons into multiple level of low energy quantas that can be converted more efficiently, as well as it requires the pasting together of these low energy photons in the near infrared that are otherwise not converted at all. So these are the detailed devices they have discussed in this article, and this was the summary. So now let's move towards the other things in detail what they have discussed. So we all know that silicon, crystalline form of silicon is the most important form of the semiconductor silicon material that has been used for electronics and photovoltaics these days, in abundance because of its advantageous properties such as the availability of large single crystals, high purity, and effective conductivity, the matching insulator, and the most importantly, it is available in abundance in nature. Similarly, for photovoltaics, if we see from the photovoltaics point of view, silicon has the 1.1 electron, crystalline form of silicon has the 1.1 electron volt band gap, which is optimal for capturing the solar spectrum using a single junction device. But this is not the case for the photonic industries. For photonic industries, we already know that there are two constraints that are limiting the use of silicon to in the photonic industries. The first one is if we use silicon as a monatomic crystal, its limited degree of freedom for to manipulate the optoelectronic properties is the first constraint. And the second one is the indirect band gap, which prevents the efficient emission and absorption of light. So we can say that the silicon technology is already developed to its maturity for microelectronic industries, but for photonic industry, high performance in all aspect of optical functionalities is highly desirable. So we believe that these nanostructures that we have discussed in the previous slides, they offer a range of opportunities for all those application areas, and they can herald a new era of silicon photonics and photovoltaics. So in communication, the silicon nanostructures, uh, we know that in optical communication system uh, is well established uh, for efficient data transfer for long distances such as internet, for short distances between board to board or rack to rack, but it is not established yet for the on-chip communication. So for on-chip communication, we still rely on the data processing based on the electronic circuits. So, in order to introduce the on-chip communication in photonics, we have some requirements. The first one, we should require the nanoscale optical sources. Second one, the optical circuits and detectors to encode, and the third requirement is the transmit data around the chip. So there are numerous impressive methods that has been discussed in this in literature that are mainly based on the nanoscale engineering, have been developed to the extent to extend the capabilities of silicon. So these methods are either based on the electronic properties or they are based on the photonic functionalities. So these methods are used to manipulate either the silicon intrinsic electronic properties using quantum size and surface effects, or they can add photonic functionalities through wavelength scale nanostructures such as photonic crystals. So let's see the for for manipulation of electronics properties. As we have discussed earlier, silicon nano crystals they have been used, and because the silicon nanostructures they offer a strong carrier confinement and the modification of energy levels through quantization, and they also enables they also has the ability to use their surface as a further design parameter. This has led to truly remarkable absorption or observation of photoluminescence level for these nano crystals that are comparable to those of direct band gap quantum dots. So similarly, the silicon nanowires, they have they offer interesting alternatives as they combine the strong confinement with readily available conduction path. But the limitation is that they require the reliable and purity-free growth methods, which are still under the developments. And for photonic functionalities, the photonic crystals, for regarding the wavelength scale photonic nanostructure, photonic crystals have proved their values as a part of photonics toolkit. In addition to enabling some of the smallest and the lowest power modulators for communication applications, they offer the highest pulsar enhancement of the known resonance systems. But the main issue is the high surface recombination velocities, which occur due to the surface damage incurred during fabrication process. So here, that's it. And now, after discussing these, they have mentioned about the photonic crystal, which is the main device that brought up to the new applications. So what are the photonic crystals? In actual photonic crystals, they are the periodic structures, also known as photonic band gap structures, and their size is of sub-wavelength. So they have the band gaps that forbidden the propagation of certain frequency range of light, and they enables control of light with amazing facility, and they produce amazing effects. These photonic crystals, they are already present in our nature. You can see those photonic crystals in the butterfly. By you can see in the butterfly here the material is the photonic crystals, and similarly in the peacock feather we can see those photonic crystal structures. So in the here we have shown the 1D, 2D, and 3D photonic structures, photonic crystals. Photonic crystals can trap light either in the cavities or in the waveguides or in the form of wires. And they act as an optical insulator for holding and controlling of light. if we do the comparison of electronic and photonic crystals, we can see that the, the atomic structures of the electronic crystals like diamond shape, and here we can see the diamond lattice for the dielectric spheres for photonic crystals. And if we see the wave propagation with respect to frequency, here we can see the band gaps for certain frequency. The photonic crystal do not allow the photons of certain frequencies to pass. And in terms of here electron band gap structures, you can see that electrons of certain energy level at certain energy levels are forbidden to pass. So they are similar and equivalent to the electron band gap structures. So in the end, they have discussed some of the perspectives of the silicon and nanostructures. Silicon nanostructure have developed with the concept of light emission and propagation, but they can also be used for light absorption in solar cells. So this is the main idea in terms of instead of using the silicon nanostructure for emission and propagation, we can use the silicon nanostructure for light absorption in solar cells. And similarly, since the silicon is viable material and it is available abundantly, so by improving the its light trapping properties, we can have we can have we can enable some other exciting applications for silicon. But the main challenge is to implementing light trapping design is the electrically viable materials. And to ensure that the design can be realized, we require large areas, and we have to be keep in mind the cost. These devices should be cost effective. So another interesting approach is from design perspective. If we see, an exciting question could be raised at whether the Lambertian limit can be beaten across the relevant solar spectrum using these nanostructures or not. So if this limit can be exceeded, so this would provide a further boost to solar cell efficiency. So these are some perspectives of the nanostructures. So this is it from my today's presentation. If you guys have any questions related to this presentation, you can comment on the video link given in the description of the YouTube. And I have tried my best to explain this article. I hope you guys have understood the main concept that has been presented in this article. Thank you so much. Take care. Goodbye.